Welcome to This Explainer. Today, we're taking a seriously wonderful journey through history to see how a mysterious spark in the sky became the literal lifeblood of our modern world. I mean, think about it. For thousands of years, humans just looked up at lightning and figured, well, that's just nature getting angry. Nobody had any idea that this exact same flash of light would one day dictate the entire fate of human civilization. It's a completely wild story of curiosity, and we're going to unpack exactly how we got from the ancient world to the smart devices you're using right now.
All right, so here's our roadmap for today. First, we'll look at nature's mysterious sparks. Then we'll dive into continuous power and batteries, followed by electromagnetism and generators. After that, it's the famous war of currents, the journey the electricity takes to reach your home, and finally, we'll peek into the future of power. Let's get into it.
Let's start at the very beginning with Section 1, Nature's Mysterious Sparks. It is crazy to think that it took over 2,000 years to go from just noticing a spark to actually making one on purpose. It all started around 600 BC. The ancient Greek philosopher Thales was playing around with amber, which, is just sticky tree resin fossilized over millions of years. He rubbed it with wool and noticed it started pulling in light stuff, like dry straw. Fun fact, the ancient Greek word for amber was electron, which is exactly where we get the word electricity. Fast forward a massive leap to the 16th century, an English scientist, William Gilbert, comes along and proves it wasn't just an amber thing. Glass, wax, diamonds, they all did this too. Electricity was finally becoming a real science. And then, boom, 1663. German scientist Otto von Guericke builds this big sulfur sphere, spins it, rubs it, and generates static electricity on demand. We were finally making our own sparks.
Now, what's really fascinating here is what happened in 1729. A scientist named Stephen Gray proved that electricity could actually travel. He sparked up some static in a glass tube, connected it to a long copper wire, and literally watched the charge flow right from one end to the other. He started testing all sorts of materials and realized that metals like copper and iron, they let the electricity flow super easily. We call these conductors. But things like glass, wood, rubber, they totally blocked it. Those are insulators. Honestly, this one single discovery laid the absolute foundation for every electrical wire we rely on today.
And this perfectly brings us to Benjamin Franklin. He's the guy who brilliantly connected the terrifying, raw power of the sky directly to those tiny sparks scientists were making in labs. You've probably heard the story. 1752, middle of a storm, he flies a silk kite with a metal key attached. When sparks jumped from that key, he proved, without a doubt, that lightning was just a massive, natural electrical event. But he didn't stop at theory. He turned around and invented the lightning rod, just a simple metal pole that grabs a lightning strike, guides it safely down a wire, and buries it in the ground. For the first time ever, humanity had literally tamed the sky to protect our homes.
Which brings us to Section 2, continuous power and batteries.
So by the end of the 18th century, we understood sparks. But the next massive hurdle was figuring out how to keep that energy flowing continuously. And it sparked, pun intended, this highly dramatic scientific debate. In 1780, Italian scientist Luigi Galvani accidentally touched a frog's leg with a metal wire, and the muscle twitched. Wild, right? He basically concluded that living bodies had this built-in animal electricity. But Alessandro Volta? He totally disagreed. Volta stepped up and proved it was actually the reaction between the different metals, not the poor frog, that created the charge. In 1800, Volta stacked up plates of copper and zinc, separated them with cloth soaked in salt water, and boom, this voltaic pile created a steady, continuous chemical current. Volta literally invented the world's first battery, the great-grandfather of the one keeping your smartphone alive right now. Having completely solved the problem of continuous power, a new, totally game-changing question popped up. If chemicals can create a steady flow of electricity, could a magnet, an object with its own invisible pushing and pulling force, could it do the exact same thing? Let's dive into that in Section 3. Electromagnetism and generators. Okay, so three brilliant minds essentially formed the holy trinity of electromagnetism. It kicked off in 1820 when Denmark's Hans Christian Ørsted noticed something weird, a compass needle mysteriously deflecting when it got close to a live electrical wire. He proved that an electrical current actually creates a magnetic field, mind-blowing at the time. Then, French scientist Ampère dug deeper, proving that electric currents can attract or repel each other just like physical magnets do. Finally, in 1827, Germany's George Ohm locked down the math. He figured out that if you bump up the voltage, the current goes up, but if you increase the resistance, the current drops. That's Ohm's law, folks, and it is the absolute bedrock of all modern electrical engineering. Now, what's really wild is that this next principle is literally the beating heart of every modern power plant on Earth today. Michael Faraday asked a simple question. If electricity makes a magnetic field, can a magnetic field make electricity? In 1831, he took a magnet and just physically moved it inside a coil of copper wire. That invisible changing magnetic field actually pushed the electrons inside the copper, creating a current. He generated electricity without a battery. This, right here, is electromagnetic induction.
And this was the huge leap from theory to reality. Because of Faraday's discovery, humans no longer needed expensive chemicals to make power. French scientist Hippolyte Pixii built the very first practical generator. Later on, Zénobe Gramme took it even further, inventing a commercial DC generator with a ring armature that pumped out super stable, continuous power. The secret was out. You didn't need chemicals anymore. You just needed to spin a machine.
With generators ready to go, electricity became big business. Welcome to Section 4, the War of Currents. So, in 1882, Thomas Edison opens the Pearl Street Station in New York, the world's first commercial power station. He was delivering direct current, or DC, to homes and shops. But DC had a massive, massive flaw. It just couldn't travel very far without huge energy losses. You'd basically need a power station on almost every street corner. Enter Nikola Tesla, a brilliantly eccentric young scientist. In 1888, he proposed alternating current, or AC. The beauty of AC? It could be easily stepped up to incredibly high voltages using transformers, meaning it could travel hundreds of kilometers super efficiently and then be safely stepped back down for home use. The ultimate engineering war was officially on. This epic debate finally came to a head in 1895 at Niagara Falls. The world's first massive AC hydroelectric plant was built, using the sheer brute force of falling water to spin these giant turbines. And it worked perfectly. They successfully transmitted AC electricity a staggering 40 kilometers away to the city of Buffalo, New York. It proved once and for all that Tesla's AC system was absolutely the superior, more affordable way to power our sprawling modern world.
So the tech was perfected, but how does it get to you? Let's look at Section 5, Journey to Your Home.
Okay, let's trace this physical journey step by step. First, at the power plant, whether it's hydro, thermal, or nuclear, a turbine spins a generator. But before that juice goes anywhere, it hits a step-up transformer. The voltage is absolutely cranked up here so it can travel efficiently across the high-voltage transmission lines, basically the massive highways of our national grids. Once it finally reaches your city, it enters a substation where the voltage is safely stepped down. Then it cruises through local distribution lines right to your house, passes through your energy meter, which, calculates your bill, and finally goes through your miniature circuit breaker to keep your house safe from short circuits. You just walk in, flip a switch, and darkness instantly turns into light. It's like magic, but it's pure engineering.
But the story is far from over. Moving on to Section 6, the future of power.
We are now at a point where modern tech is completely rewriting the rules of the game. Take solar panels, for instance. Unlike coal or hydro, there's no spinning magnet. There's no generator at all. They use the photovoltaic effect to convert sunlight directly into electrical energy. And since the sun isn't shining 24/7, we're leaning heavily into advanced battery storage to bank all that power. On top of that, we're integrating smart grids and artificial intelligence to instantly balance supply and demand across entire nations. We're making the flow of electricity smarter, faster, and way more efficient than ever before. As we wrap up this explainer, I really want you to consider this. Thousands of years ago, humanity just looked up at a random spark in the sky and asked, "What is that?" Today, that single, simple question has evolved into the literal lifeblood of our modern world. It powers every hospital, every factory, every single smartphone and computer. Electricity isn't just some cool invention. It is the ultimate proof of human curiosity. It shows our courage and our absolutely relentless drive to understand the universe around us. So, if a spark in the sky led to all of this, what do you think we'll discover next? Thank you so much for joining me on this incredible journey. Stay curious.